Welcome dear students once again into the class of number theory, and here we are dealing with continued fractions. In the previous videos we have dealt with finite simple continued fractions, and now we are moving towards infinite simple continued fractions. So a continued fraction a naught plus 1 upon a1 plus 1 upon a2 plus 1 upon a3 plus 1 upon a4 plus 1 upon and so on, which is not going to end, is called an infinite simple continued fraction. Here the number of these ai's is not finite, these are infinite. So such an infinite continued fraction, we denote it or we write it as a naught, then a1, a2, a3, an, and so on, because we don't know the last convergent, the last partial quotient in fact. So this is your infinite simple continued fraction. And interestingly, you have seen in the previous video that rational numbers are being represented by simple finite continued fractions, and every simple finite continued fraction represents some rational number. Here the process is going to change. We will show that every infinite simple continued fraction represents an irrational number, and converse also. That means every irrational number can be expressed as an infinite simple continued fraction, and we will give examples as well in this video. So I am going to start this video with theorems on infinite simple continued fraction. The first one is theorem: an infinite simple continued fraction gives an irrational number. Earlier we have seen that if it is finite, then it gives a rational number. Now it is infinite and it will give irrational number. Let us see how. So we are moving on to the proof. Let there be some infinite simple continued fraction we will start with, and then we will show that let x naught, x1, x2, x3, xn, and so on, let it be an infinite simple continued fraction. Let value of this simple continued fraction be x. Suppose that the value is x. We know that if n is any number, then your partial quotients which are even, x0, x2, x4 and so on, they will give you a monotonically increasing sequence, and the partial quotients x1, x3, x5 and so on, that means odd numbered partial quotients, that they will give you a monotonically decreasing sequence. And you know that from the previous video that this x, the value of this continued fraction, it is greater than every even numbered partial quotient, and it is less than every odd numbered partial quotients. So let n be any, let n be an even in positive integer, even positive integer, then as we have discussed in the previous videos, your Cn will be less than x, this value, and this will be less than Cn plus 1, because n is even. Value of the simple continued fraction will be greater than Cn because it is greater than every even numbered partial quotient, and will be less than Cn plus 1 as n plus 1 is odd and the value of the finite simple continued fraction, infinite simple continued fraction is less than every odd numbered partial quotient. Now subtract Cn throughout from this inequality. So Cn minus Cn will be 0. Here you will get x minus Cn, and here you will get Cn plus 1 minus Cn. I have subtracted Cn from each term of this inequality. And since it is on the positive side, 0, x minus Cn, this, so each of these numbers is definitely positive. So you can take mod. You can take mod here as well. Now, your Cn, the nth convergent is Hn upon Kn. So I am replacing the value. So it is 0, x minus Hn by Kn is less than Hn plus 1 by Kn plus 1 minus Hn upon Kn. And now your Hn and Kn, they are positive integers. They are positive integers. So you can multiply this inequality throughout by Kn to remove Kn from here. So you will get 0 multiplied by Kn is 0 is less than, here you will get mod x into Kn minus Hn is less than, on the other side your Kn, you will take LCM from here and Kn will be cancelled out. Kn plus 1 will be there in the denominator. Kn plus 1 in the denominator, and in the numerator you will get Hn plus 1 Kn minus Hn Kn plus 1. And you know that the value of this is minus 1 raised to the power n. Whether n is even or positive, you are having here mod, so definitely the value will be 1. So it is 1 upon Kn plus 1. Okay, so what you get? 0 less than xkn minus Hn is less than 1 upon Kn plus 1. What we want to show is that your x is irrational. On the contrary, suppose that your x is rational. So what we will do, taking x to be an irrational number, we will arrive at some contradiction which will show that our supposition was wrong, and hence it will be proved that x is irrational. So on the contrary, let if possible x be irrational. Suppose it is a rational number, and you know that every rational number x can be written in the form p upon q, where your p is an integer and q is a natural number. So you can replace x here. So 0 is less than mod p upon q kn minus hn is less than 1 upon kn plus 1. As I have stated that p is any integer and q is a natural number. So natural number means positive. So you can multiply this inequality throughout by q also. So multiply it by q. What you will get? You will get 0 less than pkn minus qhn is less than q upon kn plus 1. Now look at this 1 upon kn plus 1. This kn is a sequence which is monotonically increasing. So you can choose n to be sufficient large, because as your n will be large, your kn plus 1 will also be large. Your kn is actually approaching towards infinity. It is continuously increasing. So you can take n to be sufficiently large such that your q upon kn plus 1 is less than 1. Choose, I am writing here, choose n to be sufficiently large so that q upon kn plus 1 is less than 1, and use it here now. No need to put mod here. This is less than 1. So this quantity is less than 1. So what you are getting from this step? You are getting from this step that this quantity, that P Kn minus Q Hn mod is less than 1 but is greater than 0. Your P is an integer, Kn is an integer, Q is an integer, Hn is an integer. So that means this is an integer. An integer which lies between 0 and 1, which is a big contradiction. Because there is no integer between 0 and 1. So it is not possible. So we have some contradiction. And why this contradiction? Because our supposition was wrong. And what we have supposed that x is rational. So x cannot be rational. So we have shown that, we have proved that this infinite simple continued fraction represents an irrational number. Now, how to find that particular irrational number? For that, we will learn in the next videos about periodic continued fractions, and then we will move on to how to convert a periodic continued fraction into an irrational number, but that is the secondary job. Next, I am going to show that every irrational number can be represented as an infinite simple continued fraction. Now next theorem is every irrational number can be represented as infinite simple finite continued fraction. An infinite simple continued fraction. So this we are going to prove now. Proof is easy. Let x be an irrational number. The process is very easy and is very interesting as well. Your x is an irrational number. Every irrational number has an integral part and a fractional part as well. So let the integral part of x be a naught, and let the fractional part be b naught. For example, if you are dealing with root 5, what is its integral part? The integral part is 2, and the rest of the part is under root 5 minus 2, which is fraction, which is the fractional part. And since this is an irrational number, the fractional part must also be an irrational number. This is an integer. You have excluded an integer from an irrational number, the remaining part will definitely be irrational. So that means this b naught is irrational, and the fractional part is always less than 1, is greater than 0 but is less than 1. So that means this b naught is less than 1. Now you can write it as a naught plus 1 upon b naught. Since your b naught is less than 1, 1 upon b naught is greater than 1. And since 1 upon b naught is greater than 1, b naught is irrational, its reciprocal will also be irrational. So 1 upon b naught is an irrational number which is greater than 1. And if you are having an irrational number which is greater than 1, once again it will have two parts, integral part and fractional part. So this 1 upon b naught can again be written as its integral part a1 plus its fractional part b1. Since b1 is the fractional part, once again it is less than 1 and is irrational also. You can write this b1 once again as 1 upon b1. Since b1 was less than 1, 1 upon b1 is greater than 1. Since b1 is irrational, 1 upon b1 is irrational. So 1 upon b1 is an irrational number which is greater than 1. So once again it will have its integral part, say a2, plus fractional part b2, and continue the process. Continuing the process, you will get 1 upon a3 plus 1 upon, and so on. Next, what we want to show that this process will go infinitely. It will not terminate, because we have to show that it is an infinite simple continued fraction. How to show that? That's very easy. Suppose, if possible, this process terminates somewhere. Suppose if it terminates somewhere, it will become a finite simple continued fraction. And in the previous video we have shown that every finite simple continued fraction represents a rational number. That means it represents a rational number, which is a contradiction because we are given that x is irrational. So that means this process will never end and it will become an infinite simple continued fraction. So that means every irrational number can be represented as an infinite simple continued fraction. And how to obtain that? How to obtain that? Suppose, let me take any irrational number. Let me take under root 33. I want to find the infinite simple continued fraction which represents this number under root 33. And the process is same as we have just covered in the previous theorem. Under root 33, what is its integral part and what is its fractional part? Since it is greater than under root 25 and is less than under root 36, that means it is greater than 5 but is less than 6, so its integral part will be 5. And you can write it as under root 33 minus 5. This will be its fractional part. So write it as 1 upon under root 33 minus 5. And rationalize this portion now. Rationalize means multiply and divide by under root 33 plus 5. So when you will multiply, you will get here under root 33 plus 5, and in the denominator you will get 33 minus square of 5, 25. So what you will get? You will get 5 plus 1 upon under root 33 plus 5 divided by 8. Now look into this number. Under root 33 means 5 point something. 5 point something plus 5 means 10 point something. 10 point something divided by 8. 10 point something divided by 8 means 1 point something. If a number is 1 point something, then its integral part will be 1. So you have to separate once again its integral and fractional parts. So what you have to do, its integral part 1, write it here 1 plus and minus 1. Minus 1. And simplify this portion. So what you are going to get is 5 plus 1 upon 1 plus under root 33 plus 5 minus 8 means minus 3 over 8. Now this is fractional part is less than 1. So what you have to do? Take it into the denominator. So it will become 5 plus 1 upon 1 plus 1 upon 8 upon under root 33 minus 3. And once again rationalize. Rationalize means multiplied by under root 33 plus 3 and divide by the same. And divide by the same means a square minus b square. So here you will get under root 33 will become 33 and square of 3 will be 9. So what you will get, I'm writing it on the top. So it will become this 5 plus 1 upon this 1 plus 1 upon, you are going to get here 8 under root 33 plus 24 divided by 33 minus 9. 33 minus 9 is 24. So no need to open the bracket. In fact, it is 8 under root 33 plus 3 divided by 24, and this will be cancelled. 3. So it is 5 plus 1 upon 1 plus 1 upon under root 33 plus 3 divided by 3. Now this is under root 33 plus 3 upon 3. Under root 33 means once again 5 point something. 5 point something plus 3, that means 8 point something. 8 point something divided by 3 means 2 point something. So its integral part is now 2. So 2 plus and minus 2, and once again we will simplify the fractional part. So taking LCM 3, it will become under root 3 plus 3 minus 6, so it will become minus 3. So this will be on simplification. Once again, this is the fractional part, so can be taken into the denominator. So I'm changing here, I'm writing it as 1 upon 3 divided by under root 33 minus 3. And once again the same process, rationalize, multiply by under root 33 plus 3 and divide by the same means a plus b into a minus b, that means a square minus b square. So it is a square is 33 minus 9, and 33 minus 9 is once again 24. So it is cancelled. You will get here 8. So you will get 5 plus 1 upon 1 plus 1 upon 2 plus 1 upon 33 under root plus 3 divided by 8. Now it will be a question in your mind when to stop the process. The process will be stopped only when this number or this number or this number or any of these numbers which are coming will be repeated. Only on that stage this process will stop, because we will get some number that is being repeated once again and again, and it will become a periodic simple continued fraction. So let us continue. Once again it is under root 33, 5 point something. 5 point something plus 3 is 8 point something. 8 point something divided by 8 is 1 point something. So that means the integral part is 1. 1 plus minus 1. And minus 1 means, once again simplify by taking LCM. 8 will be the LCM. 3 minus 8 will become minus 5. So you will get minus 5 here, and this will be the fractional part. And fractional part once again we will take into the denominator. So it is 1 plus 1 upon 8 upon under root 33 minus 5. And now you know what to do. Rationalization once again. So multiply by under root 33 plus 5, and dividing means a square minus b square. 23 minus square of 5 is 25. So what you are going to get in the next step? In the next step we will start from the initial stage. 5 plus 1 upon 1 plus 1 upon 2 plus 1 upon 1 plus 1 upon here 33 minus 25. It is 8, and 8 is there also, so it will be cancelled. You will get 1 upon under root 33 plus 5. And this under root 33 is 5 point something, plus 5 is 10 point something, and 10 point something means the integral part is 10. So you will have 10 and minus 10 inside. So you will get 5 plus 1 upon 1 plus 1 upon 2 plus 1 upon 1 plus 1 upon what you will get now. You will have here 10 plus this will be cancelled, 33 minus 5. Take it into the numerator. 1 upon under root 33 minus 5. And this is a repeated step which you have got 2 steps earlier, 2 steps back when you got here 1. So what will happen? This 1 and 10 will be repeated now. So you will get 1 upon 1 plus 1 upon 10 plus 1 upon 1 plus 1 upon 10 plus 1 upon 1 plus and so on. This process will be continued. So this number under root 33 becomes the infinite simple continued fraction 5, the integral part, and then you will get this 1, 2, then 1, 10, 1, 10, 1, 10, 1, 10, and so on. This will be continued infinitely. Now this 110 is repeating again and again, 110, 110, 110, 110. So what we do, we write it as 110 bar. We write it like this. That means this 110 is being repeated again and again. And in this form, this continued fraction is called a periodic continued fraction. So here, how to write an irrational number into a periodic infinite simple continued fraction. And now let us have an example on the reverse process. Reverse process means an infinite periodic simple continued fraction is given to you and you are to obtain the irrational number represented by that. Suppose I am taking this number 2, 1, 3, 2 bar. 3, 2 bar means 3, 2 is being repeated. 3, 2, 3, 2, 3, 2, 3, 2 and so on. I am writing, let this number be x. Then x is 2, 1, y. Where? What is your y? Your y is 3, 2 bar. That means your y is 3 plus 1 upon 2 plus 1 upon 3 plus 1 upon 2 plus 1 upon 3 plus 1 upon 2 plus 1 upon and so on. Look at this number very carefully and look at this number carefully. Is it not the same y? Yes, it is the same y. So you can replace this portion by y. So I am deleting it from here and writing here y. And now simplify. So it is y is equal to 3 plus y upon 2y plus 1. That means y into 2y plus 1 is 3 into 2y plus 1 plus y. That means you can say 2y square. 2y square from here. Then y, this y and this y will be cancelled out. This is minus 6y. Minus 6y. And this plus 3 will become minus 3 on the other side. So it is minus 3 is equal to 0. Okay. So what is the solution of this quadratic equation? You are having a quadratic equation ay square minus by plus c is equal to 0. So the solution, you know that y is equal to b square plus minus b plus minus under root b square minus 4ac upon 2a. So the solution here is y is equal to 6 plus minus square root b square 36 minus, will become plus because it is negative here, 4ac, 4 into 2, 8 into 3, 24, divided by 2a is 4. So your y is, since this is greater than 6 and 6 minus something greater than 6 will be negative, and your number is not negative, it is positive, so you can get rid of this minus sign because the number is positive. So it is 6 plus minus, it is under root 60. Under root 60 means 2 under root 15 divided by 4. No negative sign needed now. So this 2 can be taken out as common and cancelled. So it is 3 plus under root 15 divided by 2. This is the value of y. But we want x. So I'm moving on to finding x now. We have obtained y and now we are moving on to finding x. X is 2 plus 1 upon 1 plus 1 upon y. Value of 1 upon y you can obtain from here. So value of 1 upon y is 2 divided by 3 plus under root 15. And now it's an easy process, simple process to simplify it. 2 plus 3 plus under root 15 divided by 5 plus under root 15, and once again 5 plus under root 15 will be LCM. 2 into 5, 10 plus 3 is 13, plus 2 under root 15 plus under root 15 is 3 under root 15. So this is your x. This irrational number is being represented by this periodic simple continuous fraction whose integral part is 2, rest of the numbers are 1, 3, 2, 1, 3, 2, 3, 2, 3, 2 and so on. So here I am going to stop this video here. In the next video we will have more and more concepts on continuous fractions. Till then, thank you once again.